Okay, you guys know Guangxu. He did a great seminar last time.
Wait a minute.
And yeah, I think we can go.
Okay, wait. Wait a minute. I think I should leave the room and to.
Oh, what happened? So he realized he has to leave the room to do something, and then I think he'll join me. Okay. Oh, Shaknik is here also. Hello, Shaknik.
Okay, bye. Okay. Start. Okay, okay, I just start to talk. Hello, everyone. Today, I'm going to talk about the communication neural bonds of cognition problem via identity increment algorithms. This is a joint work with Jiafeng Zhang. I'm Guangxu Yang. I'm from University of Southern California. So today, first I will introduce the cognition problem and the motivations. Second, I will introduce some previous results, and I will give our contribution and applications. And last, I will give our proof. So first, I give a definition of cognition problem. This is a query version. The query version is common used in quantum query complexity or cryptography. That is, you have an input Z, and every time you query a coordinate, then the goal is to you should output the condition. That is, there is a pair I and J, Zi equal to Zj. Then is the query version, and it's widely used in different areas. So also we know that when m equal to 2 times n, there must exist a condition. So the natural question is whether we have a communication version. The natural communication version is that for each Zi, Alice holds the half bit of Zi, Bob holds the second half bit of each Zi. So this is the collision problem we consider. So let m equal to 2 times n. N is hold the inputs, and each element is from square root n. Bob also have m elements, each element from square root n. And the goal is to find a condition that is the ij such that xi y equal to xj yj. That means that xi equal to xj, yx to yj.
So why root n?
Y square root n. That is because we consider the from query version.
The bits. Oh, I see the bits. They have half the
from
bits.
query version,
Wow.
Zi is from n. So
got
n is for the half bit of Zi. Bob hold the half bit.
Yes.
Yeah. So this is why you square root n. Yeah. And in this condition, m equal to 2 times n. So there must exist a condition in this problem. So any question about this deviation?
Wait, why 2n and not n plus 1?
You can consider different version. M equal to 2 times n or m equal to n plus 1. But different version will have different lower bounds. And different upper bound and lower bounds.
I guess.
So here is some motivation. First, we find that this kind of problem called multi-state double intersection problem in cryptography. There is a paper, they show that the communication neural bonds will imply the cognition resistance of comparator for backdoor random oracle. So second motivation is from proof complexity. They find this kind of problem is called BPHP. And they also show that the communication neural bond of cognition will imply some proof system require exponential size to refuse the BPHP. So also we have some technical motivations. The first paper showed that the information complexity can't prove cognition problem directly. They don't know how to prove it. The second is that this paper use some evening theory technique, but they can't get the tight neural bond. Okay, so first we can go through the simple protocol. The simple protocol is you can consider a uniform input distribution. That is, each element of any is uniform sample from square root n set, and each element is independent. And the bubble also has this kind of input, uniform distribution. So for uniform distribution, there is a very simple protocol. That is, n just choose n to the power of 1/4 correlate with the same value and send to Bob. And Bob will find a condition with high probability by Bose paradox argument. So any question about the protocol, I will show how to prove the protocol. Okay, so the proof is that you can say Anis. This is Bob's view of Anis. But in Bob's view, if Anis sends some correlates, there is some correlate that is with same value, and the other part is very uniform distribution. So for Bob, they only need to check this part. They say the S whether they have a cognition. So since each element or each value of correlate is uniform sample from square root n set. So if S with large size with size of n to the power of 1/4, then there with a condition in S with high probability. This is by Bose paradox. Okay, any question yet?
Number. Oh, I see. You see all. Yeah. Okay.
So this is the you can remember this protocol, this proof since this will give you some intuition well how can prove lower bound. Since you know both paradox is not upper bound, it's also lower bound. So we first review private lower bounds. So based on the protocol, they conjecture that the communication lower bound of cognition is omega n to the power of 1/4. And the private result only give a weak lower bound. They show that we give a weak lower bound. And their approach using evening theory. That is the first step. They prove a communication lower bound for gated form function and using degree to negativity to prove this lower bound. And second step, they build the based on this lower bound, they prove the lower bound of cognition by reductions.
Sorry, what
BPHP is the cognition problem.
Sorry, Guangxu, what is there? So you prove a lower bound of composition of collision with what?
Prove lower bound with degree to rank negativity.
Right, but what is there? Collision composed with there?
Collision with is I think it is some gated, versatility gated. I'm not sure the line. It's a kind of gated.
Oh, I see it mentioned.
And this gated has an and or gated, something like.
I see.
I think this is
Into the one.
yeah. And using this kind of function, they prove the weak lower bound. But they also show that there is loss in
Guangxu, I'm
reduction.
still not there. So Guangxu, but you've proven an upper bound of n to the 1/4. So why is there a lower bound of n to the 1/3?
Oh, my bad. Then 1 to the.
So the first line, you say they prove the lower bound of n to the 1/3 on the communication of collision composed with some gadget.
Yeah. Since they use reduction, reduction have some loss.
No, I'm not asking about the second.
Yeah. You in here.
Yeah, so you
Yeah.
have an upper bound of n to the 1/4 and you have a lower bound of n to the 1/3. That's not possible.
No. This is for different problem.
It's a right?
Okay, this bound is for the gated form,
Ah, I see.
and this lower bound is for condition.
Oh, you're saying that this
So
gadget,
there is some reduction between these two problems.
I see. You're
And
saying
reduction
that
has
this
some
gadget
loss.
var, this gadget var is essential and it changes the nature of the problem.
Yeah.
You cannot
there
embed
have some
var in
loss.
a smaller collision gadget or something like this. All right,
Yeah.
I see.
So I want to say there is some loss in the reduction. The best lower bound they can prove is this kind of lower bound, and to the power of 1/8.
Okay. 1/8.
The upper bound that you showed, that was for the
The uniform.
uniform distribution.
Yeah. And the protocol can be extended to the general case, but I ignore here. You can extend the protocol. I mean you can extend the protocol. Not
So you can
only
adapt this
for
protocol to
distribution.
work on every input.
It's just for any case that m equal to 1 times omega 1 1 plus omega 1 times n. This kind of range. This protocol can be extended to any range. This kind of range.
Yes.
I just give a simple protocol here. Since if you consider uniform distribution is simple to analyze it. Okay, so let's turn to our contribution. Yeah, we prove the tight lower bound is almost tight. That means that the protocol based on both paradox is almost optimal.
And
So
is
we
this
have
the
some
lower bound for the uniform distribution?
Yeah, we choose the input distribution as uniform distribution.
Okay.
Yeah. So for technical contribution, we use density. We also use density reservoir partition, and but not for limited functions. Limited function. This is kind of limited function. F compose G. And we have also bypass some barrier in information conversation and lifting techniques. So based on private connection and motivations, we have some application. This is application. I just did here. Our result have some applications in cryptography and proof complexity. Okay. So let's turn to our proof outline. I think I give almost all proof details. So first, I want to say a baby version. This is the one-way communication. One-way communication, that is Alice just send one message C to Bob, and Bob need to output the condition ij, such that xi condition. So we want to prove one-way communication bound is omega n to the 1/n to the power of 1/4. Okay, any question about the one-way communication? Okay, so in order to prove the one-way bound, we first review the simple protocol by both paradox. That is, and just choose this kind of correlates with the same value as in the Bob. Okay, and this works. Since in Bob's view, there is some correlate with same value and other part is uniform distribution. So we can, so we want to prove this kind of protocol is optimal. So there is some intuition that we should normalize any protocol to this kind of protocol. That is, if I need to send this kind of correlate with the same value, this is Bob's view of Alice. So if Alice send any message, we hope that there's still some Alice view still has this similar structure. That is, there is some part is fixed The other part is pseudo-random part. This part cannot guess the condition. So Bob only can get the condition in this part. So what it wants is that let X be the random variable of input of Anis to condition on the message of Anis. Then there is a partition of X such that for each I, Xi is structured state that is some fixed part and a pseudo-random part. And the expected size of fixed part is bounded by the size of C. This is just an intuition.
Sorry.
Yeah, we want to finish. We want to formalize the intuition. So if this intuition works, we can use a proof similar to the protocol. We also instead we prove lower bound. We also use the Bauer paradox to prove a lower bound. So this means that if this intuition works, we can by Bauer paradox, Bob can find a condition with high probability for each xi. Then each xi with this kind of form. Maybe not for each xi. That is for.
So the fixed part will be fixed, and the pseudo-random part will have near maximal entropy or something like this.
Yeah. Pseudo-random part with high mean entropy. That means you can't find the condition in this part.
Yeah. Of course. Yeah.
So let's turn to the how do we achieve it. Achieve it means that we use density in through partition. I think this is a standard technique in evening theory. So first we define the dense distribution. Distribution means that D is dense on some set J, and for any subset of J, they have mean entropy. This means that they have black and white mean entropy in J, and for other part not in J, there is a fixed value that in this kind of form. That is for J they have black and white mean entropy, and for other part they fixed. So any question about this definition? Okay, I think this is an important definition in our proof. Okay, there is a different part. We say the gamma not constant. In evening theory, they say the gamma is equal to constant, equal to 0.9. But we are different. We say the gamma equal to n minus log square root n, 1 over log square root n.
It's nearly maximal actually. So the non-fixed part has to be very, very close to maximum. What does that mean?
You mean this part?
Yeah, like maximum. I don't know.
Yeah, this part this part first, each coordinate will have mean will have this is This means that for any subset, it's very close to uniform distribution.
Yeah.
Wait, but I was expecting something like n to the 1/4 or something.
N to the
I don't know. So they've communicated n to the 1/4, right? Or maybe a little less, like a little low of n to the 1/4. So you should be able to fix, like the number of coordinates that you need to fix is roughly the same as the number of bits that you've communicated.
Yeah. So this is why we try to normalize that is we want to the fixed part, the average size of fixed part is what we most of the communication complexity. Yeah, upper bound by communication complexity.
And then the rest will have high mean entropy. Yeah. Okay. So sorry. Go on.
Yeah.
You'll.
Okay. So this is the density. This is the lemma. The lemma shows that for any subset, there is a partition. That is that for each I xi there is a ii that xi is fixed in some part and is dense on other part. And we have also second condition. The second condition is used to upper bound the fixed size. That is this is a density function. Density function is the mean entropy loss of X compared to uniform distribution. So this is the condition to bound the fixed size. But I will explain it later. So first, we show how to achieve this lemma, the proof lemma. This is just a formula. I think it's standard proof in Newton theory. That is we start where X not empty. We just pick up the maximal subset I such that violate the mean entropy rate, and then at alpha I be the outcome value is such that this is violate. Then we just output the xi, and we update the x and j to continue the progress. This is the picture. Okay, if you don't familiar, if you don't familiar with Newton theory, maybe you can stop here to if you have questions. This is just a progress of how we get this kind of partition.
Sorry. So my understanding is that, so I don't understand the statement of the lemma. So my understanding is that as long as you don't have as much min entropy as you want to have,
yeah,
there will be some way of fixing some more coordinates.
Yeah, just fix the alpha I. Yeah.
Right. So so what do you mean that so this min entropy deficiency, you can choose how much you want this to be, right? Or am I wrong? The less the min entropy deficiency you want, the more coordinates you need to fix.
Yeah. We just fix the max subset that values the mean entropy rate each time. This is very simple. We just fix it.
Right. Yeah.
This is very simple progress. I think each time we just pick up the max subset that values the mean entropy condition and we fix it.
Right.
This doesn't say anything about the number of participants. Like it could be every input is one partition by itself.
Every input. Yeah. So we will analyze this progress. We will show why this progress can achieve. And this progress will depends on the mean entropy of X.
Okay, it depends on the mean, of course. Yeah.
So we prove the first part. The first part, I think is easy. Just by a contradiction. This is because every time we see, if Xi is not dense, there must exist a K such that the outcome will also validate the mean entropy condition. So I comes K also validate mean entropy condition. This is the contradict the maximize of Xi. Since every time we pick up the maximal subset. So let's turn to the second part. The second part just by straightforward calculations. This is the first I can explain what it means. This is Xi. Xi is the subset of X, and the index means that they just choose the unfixed part. Since fixed part they don't have any uniform, it is fixed. We just pick an unfixed part and to calculate the density function. So this is this is just a this first equation is just a deflation. So second equation is we do some change. We just modify this part. This is by mean entropy condition.
Yes, give me a second. So So when you say that xi is dense, you mean that on the free coordinates, right? That exactly. On the free coordinates, its density is very close to maximal. And how close? It's 1 minus 1 over log of root and like whatever constant you've given.
Okay,
right?
maybe you can come back to this part.
Yes, exactly. Where gamma, you've set this gamma to be that number.
Yeah.
Look, that basically means, right? That basically means that you want, right? But I mean, what's the maximum density? Oh, it's M, I see. M, log, I see. Okay, good. So this should.
This is the full entropy. If you don't consider gamma, this is the full entropy.
Yeah,
This
yeah.
is the for uniform distribution, they have this
Very
kind of
close to
mean.
maximum, right? So it's so maybe if the maximum entropy would be size of I times log root n, and you're saying that out of all this entropy, maybe you've lost size of I by log root n. Yeah, you maybe lost size of I.
Yeah. But I want to say in this mean entropy condition, you can't guess the condition for any part. For any to correlate.
So sorry. What you are saying is that if I have two distributions on the two halves of the indices, and maybe they're equal on the parts that have been fixed, but otherwise they have this much entropy, then for any coordinate that you pick, I will find two inputs, which on that coordinate, sorry, I will find two inputs which differ on that coordinate, I guess.
Yeah. So for any two correlate in this block, this called equal. So the condition, it has to be a condition. Since there is a high entropy, high mean entropy. The high mean entropy condition just keep for any two coordinate. They cannot be equal with very hyper weight.
Right. Okay, so you'll prove that later, though. Okay, so but I'm kind of.
Yeah,
I'm okay waiting until I see the proof.
Okay, this is the first part. This is the second part. Second part just give some density function change after you do this kind of partition. This is by calculations. Since we say the gamma we need number, we have simplified this result.
So I was kind of expecting that
we want to show that the expected size of I is small.
Right.
Using this condition.
So normally you'd be able to get size of I times log of root n, but because your gamma is very close to 1, you kind of lose that, right? So normally you'd be able to recover log root n bits of entropy for every coordinate that you fix. But you actually want the min entropy to be maximal, so maximal that you cannot recover that much.
Yeah.
Yes, okay.
So what can we get from this process? This number shows that if we choose j equal to m is the full correlate, then that p denotes the probability of each xi. Then we have that the expected of delta I is upper bound by 1. So we have that expected size you fixed for each xi you fixed some size some correlates. The expected size of fixed part is upper bound by the mean entropy loss of x. And this is just by simple calculation. Since this part is larger than 1, and this part is bounded by 1. Rather than 0, this part is larger than 1. So we have this kind of form. Okay. So this is achieve what we want, which is for any for any something, you can say this is the every anything input after the condition message, then you can achieve this kind of partition, and you fix the part every size of the fixed part is upper bound by the minimum loss of x. So I question it. So this is the we can finish our proof. So this is the same like a rectangle. This is the input of x condition. Input of any condition is a message, and we do some partitions, and xi is dense on this central set. So by number one, we can prove that the expected size is small, is upper bound by minimum loss of x. So by both paradox, if aliens can find a condition with high probability, then we must have the expected size is large. This is by both paradox. It's similar argument to the normalized protocol. Any question about this statement?
Yeah, no, I want to understand that statement. So that's kind of so I think I see. So what you're saying is that if you fixed fewer than n to the 1/4 coordinates, and in the remaining coordinates, there is a lot of min entropy near maximum.
Yeah. So you
And the
can't get the
distribution is
condition
uniform,
in the
right? So
minimum.
there's this extra thing that the distribution is uniform,
Yeah.
right? On the strings, right?
Yeah.
Then I guess that should mean that, I mean, if the set, so yeah, it's like right on this. So this is fixed and the rest is uniform, and there's a lot of
Yeah.
options,
Yeah.
right?
So you can only get the condition in the fixed part. So and Bob input is also uniform, so they must have this kind of fixed size. So compare two results. The fixed part is small, is the entropy loss of minimum loss of x. So you can upper bound the size of x. And then next is the size of uniform distribution. Or so this is all all possible input. The size of all possible input. This is the loss. Yeah.
So what is x? Is xi? Xi. Is that what you mean?
You mean x?
X is everything?
After Alice has communicated what Bob knows about Alice.
Yeah, x is the size.
Right. You want to say that that's large. You don't want to say that that's small, right?
I want to say that is small.
Huh?
If for most x is small, you will have upper bound, no lower bound. Since you should partition the full set to minus small set.
We're concluding that if Bob can answer, then X must be small.
Okay. Sorry. Yes. Got it. Yes. Okay. Sure. Right.
Sure. Since if this is small, then we should we should more communication to partition the full set to minus small set. This is for any x. Yeah. So any question yet? I think I finished the proof of one-way communication. Okay. So next turn to two-way communication rubber bond. Two-way communication, first I review the protocol tree. And this protocol tree means that for any you start with a truth table, and for every partition you should for every communication you should partition the truth table to rectangle. And the partition the truth table of left rectangle is bound to each node of the protocol tree. That means in the protocol tree, each node is corresponded to with a rectangle in right. So let's turn to our decompose algorithm. That means how we to do what we want to do in each communication round. First, communication will partition the rectangle. So we will use the density resource partition to decompose the rectangle of each node into dense rectangles. Dense rectangle means that x is dense on some set J1, y is dense on some J2. In this is dense. Dense means we fix some part, other part is uniform. For x and y. And this means that for each node, this is the rectangle. And we also partition the rectangle into small rectangles. This small rectangle is a dense rectangle. And also we have, compared to one-way communication, we have another process. This process is called leveling process. Leveling process means that we level the input in each dense rectangle that Alice and Bob can find the condition. That means for example, for y, value y, they can find the collision depends on in this rectangle. For we will level the x, y. This process is used to upper bound the success probability of Alice and Bob. Here is the claim that if the total probability of level input should be omega-1 if Alice and Bob can find the condition with high probability. This claim we will use in our proof later. Okay, this is just a big picture of our decomposition algorithm. Just we want to do in each communication round. And why we should do this? It seems like we just simulate the best protocol. We just want to fix some part every time and normalize the protocol. Be a good protocol to analysis. So first, this is what density resource partition used. You assume any speak. You have a dense rectangle. In private round, you have x is dense on G1, y is just dense on G2. This is a dense rectangle. And any speak, this will partition x0 into x and x star. So for x, y, x is not dense anymore. Y is dense on J2. So you do some density resource partition on x and get x1, x2, x3, something like this. And each xi is also dense on J1, C minus xi. So we can use this number to achieve it. This is number one, we prove the privacy. So leveling process means that after you do some decomposition, also you should level some input. This some input is bad. Is that Alice or Bob, given Alice and Bob input, they can guess the condition in this sub-rectangle. So this is a normal deflation. That is for each xi, xi is let xi be the fixed part of x. Xi is the fixed part, be the fixed part of xi. This is for example, this is the big picture. This is the xi. This is the fixed value, value of fixed part. And this is the unfixed part for xi. So we define yi be the sum. Yi means that for y equal to yj for some ij that in the fixed part in any side. Y is the Bob's input. So
sorry, not there yet. So what? Si, there's an I big for each xi. And now you let Si be the value of the fixed part, meaning
you mean xi. Xi is this is value. That's value. Yeah. This is
what is J1c?
J1. Oh, J is the cup Oh, no, my bad, my bad. This is should be G1. So G1 is the set, and G1C is the subset. Mean that should write. My bad.
Is the set J1?
Simulate the M. It's happy with G1.
Oh, J1C is the complement of J1. And
Yeah.
J1 is what?
G1 is your private dense part. It is a set of X.
Answers.
Means that X is subset of G1.
So J1 is the indices that are free when you start this round for X.
Yeah.
Is that correct?
Yeah. G1 is the free when you start this round. Yeah.
I see. J1. All right. Yes. So now you're going to fix the coordinates II. And
maybe I can go back to the private
you
round.
add those to
Right.
J1 complement. You add those what? No,
Yeah.
wait, no.
Yeah, this is G1. This is G1. Before communication, the private round, they dance on G1.
Before
and
communication on this round. Yes, got it.
On communication, they will do some partition and they
Yeah,
will
I got it.
dance on G1 subset of
Let's
G1.
see. Okay, go down.
So
Then, yes, please. So then you added the coordinates in YII to J1 complement. So now these are also fixed. And
Yeah.
the new free coordinates are J1, except the ones that you fixed thus far. Very good. Except A. Good.
yeah.
Now, SI is the thing that you fixed, and that includes what you fixed now and what you had fixed previously
Yeah.
in the ith part. Very good. And now you define YI to be the guys on Bob's side of the rectangle
Yeah.
that have a collision.
Yeah, collision. Collision in a fixed part of any. Mean you look at X1 Y. You can know each Y whether each Y can find the collision in the fixed part.
Sorry.
This I is not the same as.
I see. Sorry. Sorry. There's no parentheses between this I and J, right? There's no parentheses between this I and J. These are just two coordinates that you fixed, I and J.
Yeah, two coordinates we fix ing. Yeah.
Do you agree that there's no parentheses between this I and J, Guangxu?
No prince. What
Parenthesis.
Parenthesis.
There's no parenthesis. No, before in the same line before. No, to the left, to the left.
To the left.
No, left, down, right. I can highlight it. Right. No, to the right. Go to the right.
Go to the right.
I think it's in view options.
View options. Annotate. Yes. Here. There's no parenthesis here.
Okay, let me IG. Two coordinate.
Yes.
Coordinate J.
I and J are two elements of this set. This set is not a set of pairs.
Yeah. My bad.
Got it. Okay, thank you. So you have two coordinates in the set of coordinates that have been fixed in X, and they have the same setting, so they have been fixed to the same thing, both of them.
Yeah, that means there is a collision in any side in a fixed part. XI, yeah, this part.
What?
This equal means that there are collision in a fixed part.
No, but the fixed part is fixed, so they're all the same.
Not always same. Since you do the density partition, not always same. But the worst case is the same.
No, within XI, the fixed part is constant.
So like if you look in the rectangle on the right,
You,
The x1 portion all have s1 fixed.
yes,
The s2 portion has all s2 fixed.
yes, huh, what, sorry? Say
So the
again.
x1 portion has s1 fixed. The x1 rows all have s1 in the
Right,
coordinates. The x2 portion all has s2 in the coordinates.
correct?
And so on.
Yes.
So in the definition of yi below, I think you can
yi depends on xi. So we just every time we just define a yi for xi. This is y is for
Sorry,
xi.
I don't think that SI is what you're saying it is. I think SI is just everything, no?
Bob knows to be or in the demonstration.
So you mean the SI
Oh,
can be
no, sorry, I'm dumb. I'm saying something. It's okay. No, I now understand. I see. So now you've chosen two coordinates. Here it would be I, and here it would be J. Oh,
Yeah.
well, no.
there should be collision.
Yeah, but there should be collision. So this would be like 5 also.
Yeah.
No, that's clear.
Now this I and J, right? So now you take all the pairs I and J within the fixed things that have the same thing. And now yi is the set of y's that also agree on these same coordinates.
Yeah. This is definition of collision.
This
And
is
it's
the definition of collision. Very good, correct. So the yi's are the red ones, are they?
Y is this kind of part, and when those are fixed yi, we fix this kind of rectangle. We fix the inputs.
Huh?
Yeah. Y similar. This is the y. This is the y. I remember right.
This yi is the guys you want to throw away, right? Or mark or whatever.
Yeah.
Am I wrong?
Not bad.
Those parts are the same. Yeah.
Is that correct, Guangxu?
This is the y.
Yi's or the guys, the yi set is the set which, if you look at xi, it's the red one. It's the ones that where the problem has been solved.
Yeah.
But,
In this case, the y seem like can get the collision. This is the y. This is the y.
okay. So each of the different columns inside a single yi can have different ij's that are the solution. Right?
Yeah.
Okay, I think I understand that.
So another step is we never input in a rectangle xi y, this kind of rectangle. But we never it if it don't be never in private round. This is a king type. That doesn't mean that if you private round, we levered. So we don't lever it in the next time. We don't count the probability.
And you're right, you remove a subrectangle because the x's are fixed in these ij coordinates. So
okay. So we can continue. So we want to prove in a level process for each I, the probability of level input in x equal to times y is at the most they can bound, upper bound. This is the one we want to prove. The probability of this red part in this rectangle is small. They have upper bound. So we consider this kind of right. This is the xi. This is the y. So this is the fixed part. Then this is the total randomness. So we only consider the case that in the fixed part of Alice, Bob has some total randomness, black and white mean entropy. We only consider this case. Since for another case, either there is no condition in there, or if there is some condition, that means if there is some place is fixed, that means even though the case there is some part, what the part there is some value is fixed, but if the fixed part either have no condition, whether if the condition there be must never in private round. So we only consider this case. So any question about the argument?
Well, the fixed parts may have no collision now, but have collision. I mean, but the collision might still happen later.
Yeah, maybe I should write. The what's the case is that there be always same values, right?
Huh?
I mean, maybe this is the worst case. There is the one, they're supposed to be one. I just want to argue that we only need to consider a case that the fixed part in any side, and this part for Bauer is free. For Bauer don't fixed. It can be fixed, but we don't consider this case. Since for other case, the level of probability will don't increase, can't be better. So any question? So any question? Okay, we just want to prove lemma 2, and for lemma 2, we should consider the.
Wait. So
well, maybe should not be still be G1 and but
you're saying that the probability of adding label is at most like the number of new pairs, no? Right, the size of ij union j complement squared minus the number of size of j complement squared.
You mean
the number of new pairs that you can the maximum number of new pairs that you can possibly add.
Yeah.
That still need to be checked for collisions.
Yeah. And for each pair, the collision probability is small by mean entropy condition. They have high mean entropy in this side. Then in Y side, they have high mean entropy.
I see.
So this is small. It is the square root 1, 2 over square root n for each pair.
Okay.
So this part is just we want to argue that we just only consider this case. This case.
Wait, but then in entropy condition, I mean, there could still be a coordinate that's completely fixed or not. Oh no, because no, I see. No, it's for all subsets. Okay, good. So in particular for all pairs.
Yeah, for any pair, for any pair, you have this kind of condition to be this kind of probability to be condition, and you using union bound to bound the number of increased pairs.
Okay.
So any question here?
I guess no, that seems fair.
Okay, we just consider this case since if this case happen, either there is no collision, or if there collision, it must be never in private round.
If there is no collision, then that makes the probability even less because there.
Yeah. No collision makes the probability even less. And if there is a collision, since J, there must be some that must be neighbored in private round. Since you must fix the Bauer set privately. In private round, you must fix the Bauer side, Bauer the part in Bauer. So you must. This is why you have a collision. So we only label the input don't be labeled in private round. So any question about this argument? Here is Newton, no, here is the there is the argument that we don't label the
Yeah.
if the input don't be labeled in private round, we just label it. So we use here. Here is that if there condition in their intersection, that means there is a case that is the fixed part of Alice. Bob also fixed some value. For example, the worst case is that there is a part. This is one, and Bob also have some one in the fixed part of Alice. This means Bob can be fixed in private round.
So if it was just J1 complement intersection J2 complement, then I see that it would have been labeled earlier. But this J1 complement union II, so the I sub I set was only created when Alice was speaking, right?
Yeah, this is the fixed part of Alice. This is the fixed part of Bob. If they have some common fixed part, this is what the case. For example, here is some value in Bob's side. This is also fixed.
Right.
This is the worst case. But I want to argue, in this case, it must be labeled before. Since you can label in private round, anytime you fix Bob's side. So that means if there is a condition in this part, for example, if there is a condition in this part, the fixed, then it must be labeled in private round.
Yeah, I'm just wondering why, because can you go to the previous slide?
Okay.
I think that then they were fixed, right? Because you have these, even if you had some collision in J, C, J, only in the J's,
If
right?
it was only in the J's, then I can see that, right?
But it doesn't, I mean, so if there was a collision,
J1's in basically Alice's fixed part and Bob's fixed part, if there was a collision before Alice spoke.
right, but in the pairs, like the pairs both come from. Right, so show me again, so it's if the intersection is not empty. Well, I see, like if both pairs came from both J's.
Yeah.
Then that holds, right?
Yeah, then it would have been labeled as soon as whoever spoke
Right,
fixed it.
yes.
But the claims that would have been labeled one speaking previous, I mean, one communication previous.
Can you go down, Guangxu?
Okay, sorry, yeah. So because of the union I sub I,
No, I mean, any collision in JC intersect J2C has already been found, right?
yes.
Any condition in this part.
Even any collision in JC has been found, and any collision in J2C has also been found,
So collision
has also been marked before.
oh, you're saying any collision that
Any collision, both of whose indices are contained in the previously fixed indices without the I has already been found. Right.
Just looking at 1 second.
Yeah, exactly. Yeah, exactly. So, right, if you have a collision in the intersection of these two, in particular, both the indices are in J2C.
Right.
So they have been found before. I guess.
Okay, cool.
Yeah. So this means we just consider this case.
Yeah.
That means the condition in any part don't be found in any being both said before. So any question yet? So we can go down. Okay, this is proof online. If we assume that happened we just allow using the mean entropy condition to bound the condition probability in the Bauer side. For each ij, since y is dense on J2, so the condition probability is small. And this number is held by union bound. It just count the increased condition pairs. Okay, so any question yet? So this is the decomposed argument. Okay, we will review. Each communication round we decompose this communication decompose the rectangle. Then density partition we'll do some density partition for each rectangle, and we'll label the inputs in a density rectangle. And we want to prove two numbers. First number is that the expected side of fixed side of query in left rectangle is at most by communicated complexity. Second number is that if fixed side of query if the fixed query side is small, and the Bauer can't find the condition. So if these two numbers holds, we will finish our proof.
Yeah.
So let's turn to proof number 3. Number 3 that we want to
right?
alpha bound the fixed side.
Yeah, I think it's.
So first, we define the density function. Density function is the average density function of each all density rectangle. The density function is similar to the mean entropy loss. Mean entropy loss of each rectangle. The density function is 0 at the beginning, and in each communication round, the density function increases at most 1. And by number 1, there will decrease at most the fixed size. And this is what, and the density function always non-negative, so the expected size can be bound by CC. This is similar to the proof in one-way case. We just use the density function to keep track of each round. So, any question? Maybe we can review the definition of density function or not.
Good. I think we're
Any
good.
question?
No, this should be off. Yeah.
Okay, so we turn to number 4. Number 4 means that we should. Okay, first we have claim. Claim that the total probability of level input should be omega 1 if Einstein and Bauer find the condition with high probability. I think claim is just a back calculations. If you remember the labeling process, we just label the bad inputs. So it should be omega 1 if Einstein and Bauer can find the condition. By number 2, we have upper bound the labeled input in each communication round. This is the upper bound by number 2. So let G1 and G2 be random variable on fixed query of Einstein Bauer side, and you will take the summation in each communication round. So the total probability can be this one. Every time you increase some condition pairs, this is the total all possible condition pairs at the end, and this is the probability. So any question yet? So we have that this probability should be omega 1 based on this claim.
Right.
However, this claim don't prove the number 4.
Right.
Since there is there is a square in expectation. So we use some trick. This trick means that this is the probability. So there is an upper bound by 2. They have an upper bound. Since this is the probability, they have upper. This one quantity is the probability, so they have upper bound. So they must upper bound by the constant, meaning that every time you label all rectangles, you just upper bound by 1. You don't use any. You don't label any more. So we can have this kind of user trick to get this result. This result will imply number 4.
Oh, no, not there. No. Oh, I see. Expected maximum.
The maximum sense that this is the probability. We can actually round this quantity each time if it exceeds 1. Then this is the probability.
That's the probability, yes. So it's at most 2, got it. Wait, paragraph. Right, so that's only bigger, correct? I agree, but
Yeah, there is some complicated trick. You should
No.
round. That doesn't mean that you should modify the number 2. That means that every time the probability of level input increase at most the maximize. This should be not modified. This is you should be maximize 1 and this quantity. That means we can modify the number 2 by this kind of form. Since this is the probability, so we can upper bound by 1. So this is why we have this kind of claim.
Why is this better than the one on the left?
Do you mean this one?
Yeah, why is the right side better than that?
It says this is the upper bound by, also have upper bound by the value. So there is a claim not told, meaning that we want this is the whole, this is the even this is large. For example, this is large one. We can't argue. We can't argue that this expectation is larger than 1. This is false. But if we have this value x1 larger than 1, and we also have the max value of x is always smaller than 2, smaller than 1 or smaller than 2, smaller than 1. Then we have this claim. This is true. Right. That means this is we want to prove this we want to prove is that the expectation of J1 and J2 is large of J1's cup plus J2. This is we want it should be omega n 1/4. Right. Now we have this condition. This don't imply this is true, false, but this condition can imply. Since there is an upper bound for each value. And this is just some trick here. So if it be this one, this is 1, so this side must be large. So for this part, either J1 and J2 not is large. In large, they will be this kind of 1. Whether they will be small, but small should be large.
So I'm not understanding Guangxu, sorry. If you take a protocol where they always send the bit 1, they never speak actually, they always send the constant bit 1, right? And you run your thing, then J1 and J2 will have size 0, right?
Wait, what?
If you take the protocol,
The protocol.
you run your analysis on the protocol that always sends the constant bit 1.
Constant bits.
So Alice says nothing. She always says 1, 1, 1, 1, 1. Bob never learns anything.
Bob didn't learn anything.
Right. So in the end, the only leaf is the entire rectangle. Then you're not going to fix any coordinate, right? So the size of this J1 Oh, these are the free coordinates.
this is the
No.
fixed coordinates.
Oh, these are the fixed coordinates, right? So you never fix any
Right,
coordinates.
so I think the equal to omega one is by assuming the claim at the beginning of the proof of
Plane.
So using that.
Yes.
No, it depends on partition. If any is send some 111, they will still have some partition or right. The partition in rectangle. If there are some partition, they still have some fixed side.
No, there won't be a partition because it's always dense, so you never need to partition again. Because you learn nothing, right?
No,
And-
nothing. So you always build one rectangle, right? This program always have one rectangle, but
Yeah, exactly.
this is
Yeah.
yeah, one rectangle. But if we have this claim, if we
So this
if we
value is
want to
large,
find a
right?
condition
So
with
for the
hyperpropagation.
protocol that I just said, right, where Alice always communicates all ones, or in Bob also, J1 complement, so you never fix. So this is 0, this is 0, so this is 2. So the average is large,
Oh, okay.
right? But obviously that doesn't imply that this J is large. So something, if there was a min there or something, or some, I don't know, min, yeah, maybe, I don't know. So something.
I think that should be good.
I don't know. But if you don't have, maybe in your program, maybe Alice Bob can't find a condition with hyperpropagation.
No, they cannot, but this value is still large, and not what you're telling me is that this value being large implies that these sets are large, but it doesn't.
I think by the argument that you went through on the right side about why this right side is important, that should be a min.
Oh, this should be a min. Is that correct?
Like if it's too large, you don't want to consider it. You want to only consider two.
Min. Min, is that correct, Guangxu? It's like you just throw us off, like with his.
Oh, my bad. My bad.
Ah!
My bad. My bad.
Ah! All right, let's try
My
again.
bad. This is some kind of rounding process, which is if the probability is very large, which is pick the small one. Since this is the probability, it always can be bounded by one. This is the mean. This is mean. My bad. This is mean.
Yes,
Mean
thank
one
you.
and this one is
I
value.
really was lost. All right.
Okay,
Now,
my
can
bad.
we
My bad.
restart?
This is
So that's a min. So
very
that's
big
a min.
mistake. My bad.
Can we restart now? Because now I think I need to go over the whole thing. So
Okay,
I
let's forget
agree
it.
that if this is at least 1 and you take the min,
Yeah. Since we modify this number 2, we can mean this one. This is the 1 and the value. So at the end, we will have a max bound mean some kind of constant value and this probability.
so what's the claim? So that's always a probability.
We want to prove that this quantity is not right. You back take a side. This means J1 and J2. Oh, this curve. J2. This side is not. We want to prove this.
It is
not.
large. Omega root n, yeah, or n to the 1 root.
Yeah. So now we have this condition. We can prove it. Right?
Ah.
Yeah, since if this happen, if this is the mean value, so it must be both G1 and G2. This side must be large, right? But if it doesn't happen, every value will be smaller than 2. So you can give this kind of, this is a trick, I think. That means that if this is the expectation of squared, but this don't imply it hold. But if you have a maximized upper bound of the random variable, you can prove this.
I see.
There is a trick. There's a trick here.
Okay. I see. Okay, got it. So you're saying that the probability of success is at most this, right? So
Yeah.
you'd
Yeah.
like this value to be the probability of succeeding in a certain rectangle. But
Yeah.
sometimes this value is bigger than 1, so oh shit, what are you gonna do? Oh well, you just, if it's bigger than 1, you use the number 1 instead, right?
Yeah.
Good. Now this value, I mean, if it used to succeed with probability at least 1, and it succeeds with probability at most this, then I agree that this value should be also at least 1.
You mean this is the 1? It can be 1. Yeah.
Yeah, 1. Yeah, I don't see why it's 2. I don't see the 2, but maybe it's some, because 2 is 1 plus 1 and you have 2 terms, or you're doing something like that, maybe. But you're saying that, oh, so what's the probability of acceptance? At each node is at most this and at most 1, right? That's it. At each node is at most this value because you've
This is the
proven,
1.
and it's at most 1 because it's a probability, right? So if you
Yeah.
if you take the average of this, that's your success probability, and now you know it's at least 1. Good, yeah, right.
So if this is almost 1, it will hold. Since either in this case, even this with high probability, we'll finish it.
Right.
Even this with high probability, we can also argue that this hold.
Right. So okay, that's at least 1. Yeah, okay, good. If this is the value right now, choose a rectangle where this is at least 1. Right? In the, oh no, not choose a rectangle, but I can apply it. Okay, so average.
This is 1 because you can label the whole rectangles. This must be 1. Yeah. Probability, so in one.
Right. So
So
you're taking an average. I agree. So now you're taking an average of 2 things. It's either 1 or this one. If you've chosen the 1, it's because the other one is even bigger, right? Right?
Yeah.
So, but okay.
If
so
you choose the 1, the size is
uh,
already bigger.
chosen 1, the other is even bigger.
If you choose this part, you can argue this.
If you've chosen that one, it's because that one is bigger than 1.
Yeah, this is whether with high probability. This is imply with high 2 cases. What either with high probability is 1, either with high probability
Right. It's
is
the other
this
thing.
kind of value.
Right. Yeah, I see.
So
Yeah,
you have high probability with this kind of
Yeah,
value,
right.
it must be in this case.
Yeah, good. Okay, good. Got it. Yes.
Okay.
Thank you. Oh, that max. Oh, that max.
My bad. This is my bad. I don't. Yeah.
All right, go.
My
Cool.
bad.
Nice. Well done. That's a really.
This is a big
well done.
mistake, I think.
Another cute little round. Very good.
So we'll give a summary of proof. We do a decomposition algorithm in each computation round. That is do density resource partition and leveling process for each density rectangle. And number 2, we use in density argument, we use the density function, and each communication, the density function will increase, and every density resource partition, it will decrease at the fixed size. So number 4, we upper bound the fixed size of correlates. No lower bound. So this is the same like by the Bauer paradox, since we use number 2.
No? What?
Yeah.
Oh yeah, it's done.
I think in this part, we also use the Bauer paradox.
Yeah, cool. No,
Yeah,
no.
which is want to argue the Bauer paradox is not only proof in used in protocol, but also used in lower bound proof. Since the Bauer paradox is not only lower bound but also upper bound.
Yeah.
So here is the open problem. I think it's wide open. This is can you consider the NF model?
Hmm.
And
Why not? You
I
probably can,
think
right?
I connected with the private
For-
authors. I contact with the private authors. They say that if we can prove the collision problem in NF model, it will have many very important application in proof complexity.
Such as?
Yes. So I think this is wide open. Since they told me that if we can prove the collision problem in NF model, it will get the best known bound compare other method. So the open question is, can we prove it in NF model? It seems like easier to extend our model, our approach than Unity theory.
Hmm.
We already extend our approach to multi-party version. That is numbers in hand model. We can extend our approach in this kind of model.
Number
But
in periods, yeah.
numbers in hand is okay. In
Uh,
numbers in hand, we can also continue our approach when we decompose each player input and do some levelings.
Right.
So
Cool. Thank you, Guangxu. That was
this is the main open problem. I have a question.
Huh?
Do you have any interesting project can discuss?
Maybe.
Interesting
Yeah, maybe. Maybe. So let me stop in the recording. I have a question actually.